last time, we were discussing about the task specification problem. So this time, for this lecture, we're going to wrap up our discussion. Then we'll spend a little bit of time discussing some types of uncertainty. Then we'll look at some exploration methods, starting with curriculum learning, and then some methods for intrinsic motivation in the setup of RL. So last time we ended the lecture saying that it is hard to specify tasks / machines. When we give them a loss function, they end up finding solutions that are not intuitive, or that those are not the same solutions that humans would want. Right? And one thing we were looking at in the end was what are different ways by which we can align the solution which humans find and which machines find. Right? And some of the things that we considered were, data. How do we change the data? How do we change the architecture? How does optimization affect performance? And how, there could be a curriculum of tasks by which machines can gradually end up learning. So, to summarize this again, it's a one thing that we do know with deep learning is that we have powerful learners, that we have constructed deep neural networks which can fit arbitrary functions. And what we know is to tell the machine what not to learn. And that is what has led to data augmentation and domain randomization, which is pretty much, one of the most significant ways in which we are able to bias the learning to not learn bad solutions. And this data augmentation is what also makes contrastive learning work. And I mean, we discussed contrastive learning a couple of lectures back. Right? Even over in contrastive learning, you create positive pairs of images by taking the original image, applying several data augmentations, and then telling the network that all of these transformations should have a similar representation. And so we are actively telling the network all these things are similar. So this is the thing, that has worked. But one question you can also ask is, these deep networks are powerful learners, but maybe they are too powerful, right? That they are finding, they are overfitting or finding solutions which for a human might be very hard to find, right? So to give an example, if I give you a random sequence of numbers to memorize, that's going to be very hard for a human, versus it's going to be much easier for a neural network to memorize it. So one way you can think about is that maybe humans have some inductive biases or some priors which make them less powerful over all possible inputs. And so they can learn some things, but not everything. Versus today's networks are able to learn almost anything. And that is reflected in the fact that if you consider, what has happened in deep learning is we have gone from 8 to 152 layers. It's possible that, just going deeper might actually be hurting our quest for having robust solutions, having more generalizable solutions. Because all we are doing is building more powerful machines. And maybe we don't want to build the most powerful learner. And maybe what we have to do is to bias the learner to be more human-like. So just to contrast this, that if you consider the human visual cortex, the amount of processing or the number of layers which are involved in processing are only 7 to 10. If you can count the number of synapses or number of connections from your retina all the way up to your cortex, and it's 7 to 10. So the human brain is, structured in a fundamentally different way. Most of these networks are feed forward, but the brain has a lot of feedback connections. It does a lot of computation in time, And there are, this lot of other kinds of computation happening. So it's an interesting area to explore that, maybe some of these architectural things in the brain, we might think of them as artifacts and may not be really required to fit data or to build the most powerful machine learning system. But maybe, these artifacts are giving good inductive biases, which make solutions that we learn be more similar to what a human would have. So this, biology / neuroscience inspired neural architecture search is an interesting open area. And I think people also work just on neural architecture search. And the goal over there is to find new network modules. For example, like, people have looked at finding new types of recurrent units. And they have shown that the recurrent units that they can find can outperform standard recurrent units on the on some subset of tasks on which they optimize over. And there is also a trend, but the problem with neural architecture search is that the search space is huge, right? I mean, the search space of architectures is very big. So how do we meaningfully constrain the search space of architectures? So that, I think, answers to that question will lead us to new types of architectures in the future, which would be super interesting to look at. And the other line of work, which has also been happening in this area, is, saying that, well, if I have a problem and the problem can be solved in multiple ways, today's machine learning systems only find one solution. But what about we develop systems which can find multiple solutions, right? So, for example, I showed you in the last class that if you have two sets of points, there can be many linear classifiers which can perfectly classify those points. So if I use the state-of-the-art ML system, I input my data, I'll end up getting one output. By one output, I mean I'm going to get one hyperplane as the output. But could I instead have systems which can give me a whole distribution over the possible solutions? So that is another upcoming small area of research right now, which is looking at this problem. So that is to summarize our discussion on the task specification problem. Any questions or comments? If not, then we'll move ahead. Okay, so let's go move ahead from the task specification problem. So next, let's spend a little bit of time on understanding uncertainty. Now, why we are doing this will become apparent, by the ending of the lecture. Also useful to know that there are two kinds of uncertainty. So one kind of uncertainty is when I have my input data X and I have some target label Y that I'm trying to predict, but the target label can have many values. Like, when can this happen? This can happen if the system is stochastic, right? Or when I'm measuring the system, there is some noise. Or there is just multimodality in the data. Right? For example, if I say, how does a chair look like? A chair, there are multiple things which we call as chairs. Right? Or an image might have a chair and a dog, or it might also have a table. Or sometimes things are just stochastic. So one kind of uncertainty is caused by these sources. It is called as eleuteric uncertainty. There's another kind of uncertainty, which is known as epistemic uncertainty, which is saying I cannot make accurate predictions for a particular input because we don't have enough data. For example, in this curve, if you see the black points are where we have data. So our uncertainty about how accurate the predictions are is low. Versus where we don't have data, the uncertainty is high. So epistemic uncertainty is due to lack of data. And because of lack of data, we are not confident about our predictions. So I hope the difference between eleuteric and epistemic is clear, right? So eleuteric uncertainty is irreducible. This is something inherent to the system. I cannot collect more data and try to reduce it. Epistemic uncertainty, on the other hand, is reducible. If I have infinite data, there wouldn't be any epistemic uncertainty. Any questions or comments over here?
I had one question. So it's like in reinforcement learning, we've seen that like seeds matter a lot. Like initialization tends to have some effect on like the kind of predictions we get or how well like the policy works. Yeah. So like would that be sort of more closely aligned to the eleuteric uncertainty or sort of an epistemic uncertainty? Because it's like that is agnostic of the stochasticity or multimodality of the data of the sensing process, but it's not really due to lack of data as well.
So I mean, it's a slightly different angle to it. I mean, the reason being that if you look at the output that we are trying to model, the reward function, that is not really changing, right? It's just that when we estimate the parameters end up being different depending on the seed, right? So, this, I mean, I guess it becomes complicated because in this case, your data generation is depending on the policy itself, right? And I mean, in theory, if you collect infinite seeds, then you should be able to bound the performance and say, well, this is what is, I'm very confident this is the performance of my algorithm. But there's no inherent stochasticity in the system per se, right? I mean, the reward function is well defined. It's just that, when I'm learning a policy, my policy ends up learning different things. So I would put it more in the category of epistemic uncertainty because it is not got to do with my environment, right? It's more got to do with the model that I'm building. It's not an inherent property of the environment.
God. Okay, so can we say something like this, that like eleuteric uncertainty is due to the agent in the environment and epistemic uncertainty is due to properties of the agent?
So eleuteric uncertainty is the property of the data itself, right? It's like, for example, if I have a thermometer, from which I'm measuring temperature, the thermometer is faulty. That there's nothing I can do on the modeling side to correct for it, right? Because that source, the error is in the source, right? Epistemic uncertainty is due to the model, right? I mean, I could, for example, collect more data, or I could change the function class that I'm using to estimate the data, right? So if there is uncertainty due to my modeling choice, that is what is due to epistemic. That is what is called as epistemic uncertainty. If it is an inherent property of the system, then it is eleuteric.
Thanks, I've got it.
So previously, we looked at this bootstrap technique to estimate uncertainty, right? Where we said, if we have an input, we can have k heads, and we can measure the variance among k heads to estimate the uncertainty. For example, over here, there's this plot where there are these blue points, and where the blue points are not there, the uncertainty is high. And so bootstrapping was measuring epistemic uncertainty. This is what we were measuring. Now, just to drive home this point, let's do a small quiz. So we have these two diagrams in front of us. And now there's a poll which you are seeing on your screen. So the poll asks questions about the nature of uncertainty in both of these plots. So the question mark on both the plots is the point at which we want a prediction. As you're trying to do classification in both the setups, and there's a point and near the blue square, and you want to make a prediction. And the question is, can we accurately make predictions in both the scenarios, or is one of them a case of eleuteric or epistemic uncertainty? Right, so let's maybe give 30 seconds and think about it. I see we have 10 answers. Maybe a couple of you are still on the fence. Okay, I'm like 5 more seconds and then we're going to call it off. So, now is your time to pull the trigger. Okay. So let's see, what people, think. I think almost everyone thinks that the left one is an instance of eleuteric uncertainty and the right one is an instance of epistemic uncertainty. And that is correct. And over here, there is uncertainty because, at this data point, there are some data points which belong to the red class, some belong to the black class. So if I get a new data point, it's unclear what class it should be. This is not going to improve if I collected more data. This column is still going to be there. Versus in this scenario, if I get more data over here, I could increase my confidence. So, in the class, what we have looked at is how to model epistemic uncertainty. We haven't really looked at eleuteric uncertainty. But this does becomes useful, specifically when we're dealing with stochastic systems. So we will look at one class of models, which is variational autoencoders, in a few lectures from now, maybe even the next lecture, and see how do we deal with inherent multimodality / stochasticity. Some of these ideas on eleuteric and epistemic uncertainty are going to be used in some of the exploration discussion towards the end of the lecture. So I'm introducing these over here, and we'll come back to eleuteric uncertainty later. So before we move on, any questions on these definitions? No? Okay. So, let's look at one concept, the concept of curriculum learning. And the reason we're going to look at this concept is, the question is, does the order in which we give data to our agent or the tasks, does it really matter? So we know that in animals, there is a task curriculum, and it is called shaping, and it does matter. For example, if you want to teach a dog something, you do need to give a proper order of steps in which you are teaching. Or even in human learning, to do calculus, first we need to learn arithmetic. There's a curriculum which is important, right? If I give calculus before arithmetic, it can become quite tough. Or if I give calculus before algebra, learning that may not be trivial. Right? So broadly speaking, the idea of curriculum learning is to gradually present harder tasks. Start with something simple and then go for something harder. And the hope is, maybe it can lead to faster learning, or it can help us find a better optimum. So a classic paper to look in this area is Curriculum Learning by Joshua Bengio. Was around 12 years ago. It's a good introduction to curriculum learning from a machine learning standpoint. And among several results, one result that they show is that, on this task where they're building a language model, what is a language model? It is trying to predict what is the probability of the next word given some words I have in the past. So they have, so lower is better, and the x-axis is the number of training updates. The red line is without a curriculum, and the blue line is an instance where they follow a particular curriculum that first they only use the 5,000 most frequent words and only train on that. And then they slowly go and expand so that the data set increases. The reason for only training on the first 5,000, 5,000 most common words is so that you have a lot of data for them, so you can learn well. And then you go to more and more words for which data is fewer and fewer. Right? So now this is not a classical notion of hardness, but it's some notion of hardness, right? It's a proxy of increasing the complexity of the task. Now, similarly, there are many heuristics which are there in how to choose a curriculum. So one more piece of work is this teacher-student curriculum learning. The idea is, again, simple. The idea is, suppose if I have 3 tasks, task 1, 2, and 3. On the right, I'm showing the probability of sampling these tasks. So we want to sample tasks based on the learning progress. So if I'm able to learn a task, then I should sample it with higher probability. If I'm unable to learn, for example, the red task, I should not sample it. Right? So the intuition being that either some things are too easy. If they're too easy, for example, when you learn the blue task, it becomes very easy. There is no point of sampling it again. Sometimes things are too hard. When they're too hard, even if you keep on sampling those tasks and trying them, you're not going to succeed. So there is no point trying to succeed at something you're not able to succeed. Right? So you should look for tasks in which if you succeed, you get some signal of improvement. And those are the things that you should sample most often. So that's one way to construct a curriculum. And so this paper, proposes, or not this paper proposes, but this paper shows that, constructing curriculum based on learning progress can aid in some reinforcement learning tasks. And so specifically, they consider training this agent, the green guy to go to a yellow guy, and they compare their method against a baseline in which there's a manual ordering of tasks. So initially there's a simple task that just need to go to the yellow block. But then as time progresses, we have more barriers between the agent and the goal object. So what they show is that if you can compare different strategies, and one can evaluate performance only on the last task. So if you look at the training, okay, so first, let's look at the training curves, right? So training, the y-axis is a time step, and the x-axis is the time step, and the y-axis is the rewards that you're getting. Now, if you look at these different lines, our uniform sampling is green, manual curriculum is red, and their method or what we discussed is purple. Now, if you look at the training rewards, it is unclear which strategy is the best. But the training curves, the training evaluation is also unfair. Why is it unfair? Because different curriculum strategies are evaluating on different set of tasks. Right? So a uniform strategy would be evaluating on a uniform distribution of tasks. a manual curriculum at some point may be evaluating on one of these 5 tasks, right? Versus an automatic strategy might have chosen some other task at the current time step to evaluate on. If you just look at the training curves, it's not a good criteria to judge how well these methods are doing. One strategy is to look at the performance only on the last task, right? Or one task which you really care about, which is the most complex task. So if you look at the evaluation on that task, what you'll find is that the automatic curriculum learning strategy ends up doing almost as good as a manual strategy and is way better than uniform sampling. So the other way to understand this is, suppose if I give all these 5 tasks to an RL agent at once, the variance will be super high because I'm trying to solve all these tasks simultaneously. Versus if I give them in sequence, the variance is going to be lower. Because I can first easily learn to solve this task, then I can leverage this to solve the second task, and then third task, and so on. So intuitively, that is why curriculum is helping you solve tasks or learn better. Any questions on this part?
Yeah, hi, Professor. I have 2 questions. Following, because you said that curriculum learning helps in some of these RL settings. So, obviously, well, a first question is like, what can you say about those settings in which curriculum learning doesn't work that well? And if you have any idea why? And then kind of the other question is, thinking about the concept of curriculum learning kind of in an abstract way without trying to implement it, is it correct to say, or is that something that everyone agrees that for any problem, RL problem, there exists a way of learning, you can say a curriculum, there exists a curriculum that will maximize the learning ability of the agent, then maybe it is easier or it is harder to find that curriculum, but is it correct to say that that curriculum exists and it is warranted to lead to the best performance?
So I don't think there is any theoretical proof or guarantee that such a curriculum is necessary, right? I think it's more of an intuitive idea that a curriculum is going to be helpful, right? And this would specifically be helpful if the tasks that you have are correlated with each other. If there is no correlation between tasks, for example, the skill you learn in task 1 cannot be used for task 2, then the curriculum is not going to be helpful. So that's a setup where curriculum is not useful. But if there are similarities between tasks, then curriculum can be helpful. I say can be because sometimes you might want to solve 3 tasks at once, or maybe you solve the third task that makes you realize how to solve the first task better, and then you want to go back to the first task and try it again, but maybe in a more efficient way, right? So some curriculum learning strategies may not allow you to do that. So it's unclear if just a linear curriculum of tasks is always going to give you the best performance. But what you can say is that an ordering of tasks, which may not be linear, where things can fluctuate, could help you learn better than just uniform sampling.
Okay, because I'm thinking, because while you were explaining this, just thinking about maybe how different domains work on RL problems, right? I have the feeling that a lot of the researchers are prioritizing a lot how they represent the problem, like thinking a lot about representation. And I was just wondering if, maybe curriculum is something that we are not looking enough. And,
So,
and it might be another way to move forward in the real world.
so I think definitely there is a lot of work even in reinforcement learning looking at curriculum. So I'll cover, two more examples, and maybe we can take this discussion up after these examples.
Yeah, sure.
So, any quick questions on the curriculum strategies that I just discussed? If not, then I'll jump on the examples, like 2 more examples. Okay, so let's consider 1 more example, which is block stacking. Right, so in block stacking, we have these 3 blocks, for example, and the target is provided by these 3 spherical balls. So you want to place these blocks in these locations. Right? And for now, let's assume that the state space is position and orientation of the block. There's no vision involved, and the action space is position of the end effector and whether the gripper is open or closed. So if you do pure RL on this task, we do not end up succeeding at all, right? It completely fails. Why is this? Because the reward function over here is sparse, right? So why is it sparse? Because you only get a reward when you move the green block to the right location, then you get +1, then you move the yellow block, then you get a reward of +1. So you really have to get the order of the blocks correct to get rewards. And doing that long sequence of actions correctly is hard to do, especially when you are doing a random sequence of actions. So in the case of sparse rewards, for example, if I have to go from my current location to a goal location, getting the reward is tough. And as we discussed earlier, that sparse rewards are typically easy to define. That's why we define them. But many of the strategies are not going to get over there. And this is what leads to the exploration problem. Now, one thing that we have discussed in the past to overcome the exploration problem is to make use of demonstrations, where we leveraged an expert who tells us how to stack blocks, and we saw how to use these expert demonstrations to solve tasks like tower stacking. So what is the idea of task curriculum? It's complementary to an expert, right? What task curriculum is saying is, well, let me first start with a problem which is maybe easier to solve, or in this case, I start with a goal which is closer to my initial position, and then we slowly move the goal far away. So that's the idea of a task curriculum. Now, if you consider task curriculum in case of block stacking, then the curriculum might mean that let me start with 1 block and then slowly increase from 1 to 2 to 6 blocks. So you might believe that doing a curriculum like this may solve the problem. Now, it turns out that you can try RL with this curriculum, and what you end up getting is a line shown in orange. Right? So what I'm showing is on the x-axis, the number of interactions. On the y-axis, how many blocks were stacked. So despite having a curriculum, the agent only ends up stacking 1 block. So the curriculum is unable to succeed over here. So one question we might ask is, why did the curriculum fail? So one thing to note over here is that the state space with 1 block has only 2 dimensions, right? Maybe the x, y position. And as I'm increasing the number of blocks, my state space is changing. So given this fact, does anyone wants to propose or suggest a reason why the curriculum might have failed on this task? mean, feel free to type it on chat or feel free to speak up, if there's some thought that you might have. Okay. Maybe we can do some discussion later. So, or for some other question. So one thing, which can happen, one suggestion came up is curse of dimensionality. Kind of. You're getting close to that. So one thing, that can happen over here is, suppose I train this policy pi, which looks at the state space x1, y1 and produces the action A. Now, if the curriculum has to work, it means that, this policy pi needs to work on this new state space, right? But the size of the state space is different. Now, how do we account for that? Now, one way you can account for that is to maybe average the features together. So you have block x1, y1. Recall the lecture we did on recurrent networks, right? Over there, the problem was also that I have a sequence of words. The sequence of words could be of arbitrary length, and we somehow need to make them a constant size feature vector. Right? So over here, it is important to choose a good way to represent these observations, right? So it could happen that if I use a bad way or a bad model class, then when I train a policy on like the simpler problem and then take it on the more complex problem, the policy may not generalize. So the system may end up treating each problem as a different problem, and therefore no transfer may happen. Right? So as suggested on the chat, one way to deal with this is to use good methods which can represent sets of objects. One of them is a graph neural network. So this is something we have discussed before, so we're not going to spend time on it. And turns out, if you end up using a graph neural network in this case, the curriculum will work and the agent is able to go on and stack these 6 or 7 blocks. And this, one can see in the graphs also. So this green line is using the graph neural networks with the curriculum. You can also say, well, was it just a graph network or was the curriculum also important? So you can do an ablation, which is the blue line, where you can take the graph network, but remove the curriculum, right? And if you see the blue line is again fails to perform the task. So over here, both the curriculum was important, but for the curriculum to work, we needed the right model class so that there is enough transfer between different stages of the curriculum. And with this, if you consider this task of block stacking, with human demonstrations, we can get some performance numbers, but with the curriculum learning, you can do quite well. You can do much better with much fewer interactions. And if you're interested, you can look at more details in the paper where, this policy which is learned cannot generalize to new tasks. New tasks, I mean, like maybe stacking more blocks than what we trained for, or even going to new configurations, like stacking, a couple of towers, or maybe stacking these blocks into a pyramid. I mean, these things get enabled because we use a good core representation of the data, which is a graph network instead of the alternatives. So I'm going to skip some videos over here, which you can look in more free time. So what is the takeaway over here, right? So again, tying this back into the issues that we discussed with reinforcement learning. So one of the issues was, where do rewards come from, right? And what we discussed is defining reward functions is hard. Defining sparse rewards is much easier, but that leads to exploration problem. And one solution to the exploration problem is a task curriculum. Maybe designing a task curriculum is less effort than providing demonstrations. So task curriculum can work in some scenarios, right? We saw the first, like the maze example, where we use learning progress as a criteria to choose tasks. Then we looked at the second example of block stacking, where we realized that it's important to choose state representations or models which have good inductive biases for curriculum to work. So this is something which is a good takeaway to have. That curriculum can help, but you also need a good inductive bias in your model. Another caveat is that if all of your tasks are simple or are similar complexity, then uniform sampling is going to be sufficient. That curriculum typically helps where there is a gradation in task complexity. Some of them are simple, some of them are harder, but there's also an overlap between them. So this idea of curriculum was also used in another example we had seen before, which was this robot walking on diverse terrains. So we looked at this example a couple of times, and most recently we looked at it was with respect to imitation learning. So what we had looked is that this agent was trained in simulation, and we had a privileged policy which had access to all these things like contact information and so on, which is available in simulation. And we trained a teacher policy, and then we mimicked it with a policy which did not require this information. That we looked in the imitation learning literature, in the imitation learning lecture. But there was also one more detail, which is how were these terrains chosen on which this animal or on which this robot walked. So it turns out there was an automatic terrain curriculum which was used. Right? So they defined 3 classes of terrains: hills, steps, and stairs, and they had different parameters. And these parameters were varied slowly over training. Right? So initially, one can randomly sample the initial terrain parameters, train a policy, evaluate how well the policy is doing, and then re-choose the parameters depending on some criteria. That criteria could be learning progress, that criteria could be uncertainty in performance, so on and so forth. Right? Now, the exact details of what they did, I would encourage you to look at the paper. But the takeaway is that if you just trained on one environment or a couple of environments without the curriculum, this would not have worked. The curriculum was key for this agent to learn how to walk. And then this policy that it learned using the curriculum was distilled into a student policy. So this is one more example of a real world system which was trained using RL, where curriculum was important for success. And if you look in the literature, you'll find many other examples of using curriculum. The one thing which remains unclear is how to choose the sequence of tasks. And what you'll find is there's no clear-cut one tool fits all solution. There'll be slightly different solutions depending on the problem that you're looking at. And so that's one caveat which is there. So those were the examples which I have on curriculum learning. Any questions over here? Joanne, do you want to bring up some discussion points from before?
No, just I think I need to read a bit more because yeah, I there's kind of a lot of ideas like going on. So because just trying to think about which could be the best way to kind of bring curriculum learning into close to real world problems. And I'm just trying to think, for instance, so you have different dimensions of choosing the curriculum, right? So how you sample, then you in the block stacking one, right? The tasks were made more complex, but at the same time, you could have chosen another dimension of building a curriculum, which were kind of maybe easier blocks to stack, as
Yeah.
opposed and more harder, right? So, because let me put you an example of my research. Like, so I work on a molecular generation problem, and by means of reinforcement learning, right? And what most of the community has looked into when it comes to that with reinforcement learning is just the way in which we can represent the molecule, the action, the reward, and try many different things, right? And I was just saying, okay, maybe if we took a different perspective and say, okay, instead of trying to add as much complexity or as much representation power as possible, start with something easy, and then which should be the way moving forward to make this task harder and find that curriculum that would lead us to a better outcome. So that's what I was thinking about, and all of those questions were coming in, right? So if there's any research around how to find that curriculum and which curriculums make more sense with respect to the specific features of the problem.
Yeah. So yes, I think what you'll find is there are two bodies of work, right? So one body of work is which manually chooses a curriculum strategy and then shows that it leads to better performance, like the block stacking work, right? The other body of work that you'll see is automatic curriculum generation, right? And for example, this walking robot is that example. So you still have to decide on some parameters. For example, the parameters are this roughness, frequency, amplitude, and you sample, say one set of these parameters, and that set of parameters has some weight, say W0. Suppose all the parameters initially have the same weight, like whatever parameters you sample. Then you run the system, you evaluate it, right? For some parameters, you find the reward is almost zero. For some parameters, you get some reward. Maybe you resample the parameters for which the reward is increasing across episodes with higher probability, right? So if you end up doing it, then you will end up choosing terrains on which you're learning the most, right? So I think it becomes, you do need some domain knowledge over here. For example, you need to know that, okay, hills, steps, and stairs, these three things can cover a wide range of, terrains. And each of these terrains I have to parameterize with, a few things. So now, in case of chemistry, maybe if you could define, some space of molecules with, some parameters, then you could, possibly think of implementing very similar strategies as used in this work. It could be a good starting point in the investigation.
Mm-hmm. Yeah, I think that we as humans, for instance, thinking when we teach children how to do things, right? You could be said, okay, you have to maybe teach a kid how to swim or how to ride a bike or how to, and depending on the task, it's kind of immediate to think, oh, I know which is the best way in which I can teach this kid how to do this task, and probably the way is different, right? So
Yeah.
kind of the complexity and the interaction with the tools and so on, but you have kind of an automatic way of choosing a curriculum that you are very confident that's one of the best things you can do to teach that kid, right? So I'm just thinking, when we have, instead of having kids teaching different skills for life, we have like different RL agents trying to work on different domains. They can be molecular optimization, they can be, I don't know, robot walking, manipulation, and so on. Is there any good understanding or research works that kind of start from that point, right? So for these different problems, the best way to learn is not the same. So the way to build the curriculum is different. Like trying to put a layer on top of that, a learning layer on top of that, you know,
Yeah. So, yeah.
maybe it's
So
too broad. It's a very broad discussion probably, and
yeah. So I mean, unfortunately, I don't know of any work which does curriculum learning at that broad level. Although there is some work on active learning. So if you look at active learning on image classification, or just in classification setups, I think people have looked at what active learning strategy works across different kinds of classification problems. Right. So there is some studies in classification, but in curriculum learning, there unfortunately isn't like a review which goes across domains. Yeah, but I think the points that you're raising are some good points. Maybe we can take it up, later in an office hours or something, and chat more if you're interested. But these are good questions.
Yeah, I mean it's a broad area. Yeah, happy to discuss more. I think it's all of these discussions. The class next week is about real world, right? The next it's related.
Yes.
So,
yes.
Yeah.
Cool. Now, Anubhav, did you have a question?
Oh, I was just kind of on the topic of that discussion. Like it seems like one way you could do curriculum is you artificially make the task like easy, and then you relax that handicap.
Mm-hmm.
Or sorry, the opposite of a handicap, but you like are kind of relax that easiness over time. So like Juan mentioned kids learning to swim, right? Like kids don't learn how to swim just by getting dropped into the pool. They usually start with like a floaty or something, and like I guess that's kind of what's being done in the terrain thing. I wonder if in chemistry or like I mean I don't know too much about Juan's like the specifics about the research, but like if you were like looking at molecules and maybe you could relax kind of requirements on energy or something like to bind different molecules, like something like that, where if you could find a way to like make the task easy, like non-realistically easy, but then like gradually decrease that requirement over time, then you might end up with something.
Yeah, but I think in general, that's a good strategy. And one thing one needs to be careful is the same problem we saw in reward shaping. Sometimes when you make a task easy, you might end up in a local minima from which you cannot escape out. Right. So just to give an example, suppose I have to touch something. Suppose to pick up a cup, I need to grasp the cup on the side. Right. Suppose initially I make the task easy and I say my first part is just to go to the center of the cup. Right. Then my gripper can learn how to go to the center of the cup. Right. And it probably will go inside the cup. Now, if it needs to go and grasp the cup, then it needs to unlearn to go inside, come out, open the gripper, and then grasp. Right. So, so there is some unlearning that one might have to do if the task is easy in a slightly, different dimension. So there needs to be some, you could sometimes easily end up defining a curriculum which can make you get stuck in a local minimum. So manual design of curriculum, again, has some of the same issues that reward shaping has. So that's just one caveat over there. Cool. So next, we are going to look at some algorithms on exploration. But maybe let's take a couple of minutes of a break, and then let's jump on exploration. So instead of 5 minutes, maybe let's take a break for 3 minutes today, and because we have some content to cover, so let's meet back in 3 minutes, and then we'll jump back into exploration. Okay, so let's resume. So recall, we talked about the optimum exploration trade-off previously in context with bandits. And in bandits, we saw that UCB helped us make this trade-off. Then we looked at contextual bandits, and we saw how square CB was helping us make this trade-off. In reinforcement learning, until now, we have looked at epsilon greedy or entropy regularization as methods for exploration. And these are pretty much just heuristics. Now, what we're going to look at is some more advanced methods which can help agents learn to explore. Now, unfortunately, in the general reinforcement learning problem, we don't have an optimal method for performing this trade-off. So what we'll be end up discussing are some heuristics, some ideas which have known to work well in the field. So, and if you're interested in theoretical work, this is wide open problem. I think there is some recent results which have come up in case of linear MDPs, which are exciting, but pretty much it's a wide open problem if you want to analyze it theoretically. But let's look at what do we know empirically in the field. And the basic intuition which all of us have by now is if I consider an environment, if I'm doing random exploration, this random exploration is limited, right? I only cover a small space of the entire state space. So now instead of taking any action, that is instead of moving anywhere in my state space, if I could take an action which can help me expand where I have been, then I can explore more, right? So in some ways, we want mechanisms which incentivize novelty, and that will help us cover the state space, right? So one idea, one class of ideas could be that the agent is exploring the environment, right? It builds the kind of models we talked about previously. For example, it will build a forward model which says, given the state and the action, let me predict what is going to happen next. And we can incentivize actions which lead to high prediction error, right? So I can say, well, if I'm in this particular state space, if I do a particular action, my prediction is inaccurate. And therefore, I should try this action more because I don't understand this part of the environment. And if I sample those actions often enough, then my model is going to improve, my errors are going to reduce, and then I can move to the next part of the environment where the error is higher. So let's see this, with help of a concrete example. So for example, consider, this game of Mario, where we have access to an RGB image of the game. Now, if you move left, the agent moves left. If you move right, the agent goes right. If you press up, the agent presses up or goes up. If you press down, then nothing happens. Now let's consider that we were building this forward model. It says, given the image and the action, what is going to happen next? So if I press up, the prediction might be the agent is going to go up and then come down. So the prediction ends up matching reality, then everything is good, right? There's nothing to worry about. Or, right? But now consider a scenario where this agent is near this green pipe. But this agent has never seen a green pipe before. That previously, whenever it pressed the right arrow, it would predict it's going to move right. So in this case, because it has never seen an obstacle like this before, the agent also thinks it's going to go through the pipe. But in reality, it goes and hits the pipe. But there is a mismatch between what happens in reality and what the agent predicts. So suppose I incentivize the agent to take this action, which leads to a prediction error, right? Then it is possible that the agent will be incentivized to come close to this green pole because the reward is going to be high. I suppose I'd make the prediction error as a reward, and then I train up the policy to maximize this as the reward. Then the agent is going to come close to this pipe. Now, once in a while, when the agent comes close to a pipe, suppose it tries another action, which is going up, but the agent predicts that it is going to go up and then come down. But it could happen that in reality, the agent never comes down because it climbs the pipe. So again, there's going to be a mismatch between the prediction and the reality. So now, if we incentivize this agent to maybe say become curious, if you want to call it that, or just maximize prediction error, it could learn to come close to the pipe and then jump on top of it. Right? So just by maximizing a notion of prediction error or maximizing a notion of novelty, the agent can learn things about the environment. Yes, Anubhav.
So is this like you talk about maximizing this like prediction error? Is this being added to like some reward, or is this the only reward? Like
for this example, I'm showing that's the only reward.
Okay. And then like how are you able to actually complete the task that you like want to like have Mario reach the end of the level or whatever, if like there's no like it's not like there's no relationship between the task and then this reward, right? This is just like trying to explore novel scenarios.
Yes, so that's an excellent question. So now typically what happens is, these games are designed by game designers and they design them in a particular way. Right? So for example, in the case of Mario, the games are designed in a with like increasing complexity, right? So initially you kind of move without any barriers. Then you find some barriers, then you find some enemies. So if you learn to keep moving right, and you end up doing some correct things, you will end up solving the game, right? Because there's structure in how the novelty is there in these games, which were created by game designers, right? Now there could be scenarios where there's a mismatch in the novelty seeking behavior and what you want the agent to do.
Yeah.
But in many scenarios, as has been empirically shown, at least in the game of a lot of these video games, that there's a good match between the heuristics that we have come up with and the game performance.
Okay, that's interesting. Yeah, that makes sense.
So Ayush, I'll answer your question in a bit about in what space this prediction error is being measured. So, there is a lot of work in developing exploration methods, and here is just one good summary of some of the more popular systems. But let's look at the system that we discussed in more detail. So we have a current state, we have a next state, and we can build a forward model. One thing we could do is to build this forward model in the pixel space, right? And then I can call this error as the reward. But as we have discussed before, that error in the pixel space can be undesirable, right? So why is it undesirable in the case of exploration? To give an extreme example, consider you have a noisy TV. A TV, when there's no signal coming, it just flashes the screen, which is black and white pixels that you see. Now the screen is new every time you watch it, right? So if you were to make a prediction, your prediction is always going to be inaccurate, and you're going to get a high reward. So you can become curious about things that you don't care about, right? Because they are sources of novelty, but this novelty does not affect you, and this novelty is not even useful. Now we want ways which can, not get trapped by such scenarios, right? So these are also known as curiosity traps or novelty traps. So there are different ideas in the literature to go around them. Right? So for example, one prior that you can try to put is that let's only be curious about things that the agent can affect. And let's not be curious about things which I cannot change. So one way to build in that intuition is to say, well, let me learn a feature space phi which only encode things which I can affect. Right? And one way to learn this feature space is, for example, by using the inverse model. What does the inverse model say? It says, learn a feature space from which I can predict my actions. So if something is not useful in choosing my action, I'm not going to capture it in my feature space. And then we can learn a forward model in this feature space, and then have the error in my prediction as my reward. So how do these things come together? I have my current state. We are trying to learn an exploration policy which produces an action. When you take the action, we get the next state, right? And we use this data of current state, action, and next state to learn this forward model. This forward model produces the error in the prediction produces the curiosity reward. This is the reward which we can try to maximize by using reinforcement learning. And then we can ask the question, how good is this policy? Is the policy that we learned only using the reward generated by the agent, how well it performs? And this reward is many times known as the intrinsic reward. So, for example, in this game of Mario, if you do not give any reward from the game, but just maximize the intrinsic reward, you find, this agent will, jump over these, pipes, kill these enemies, in general, make progress in the game, right? So this is a paper I'm showing from maybe 4 years ago. There have been more advances. And now if you see the latest papers, it's going to, cross almost all levels of Mario quite quickly. It's all of these behaviors, jumping over enemies, pipes, killing enemies, are emergent behaviors. Now you can ask other questions. For example, you can ask a question: if I train this policy on one level, does this policy, end up generalizing on a new level? So it turns out there is some evidence that these exploration policies generalize, although the generalization is somewhat limited. Now you can take the same algorithm and try to use it, for example, in case of first-person navigation. And what you end up finding is this agent shown on the left learns to walk along corridors. Versus if you're doing random exploration, you will become stuck. Now you might wonder, why will the agent learn to walk along corridors? So the intuition is that if you want to maximize prediction error, you want to go to parts of the state space that you have not visited before, because the data coming from that part of the state space, you have not trained your models on, so your models are going to perform worse. So if you want to reach as far away as possible, the most efficient way to move in the environment is through corridors, right? So therefore, you automatically learn to move along corridors. Right? It's a consequence of the environment setup itself. Right. Now I see a few questions which are coming up on the chat. I will answer them, but give me a few minutes. Right? So that's why this agent ends up moving along the corridors. Then the other thing, I discussed about was these novelty traps. So for example, here is what I mean, by noisy TV, right? I mean, so if you look at, this, screen, this is something which can make you really curious. So what these videos are showing is that if you measure curiosity, for example, in the pixel space, that is, you're measuring your errors in the pixel space, you can become stuck because this thing is novel for you. Versus, if you end up, measuring curiosity in the feature space that we discussed about, you can ignore these new things in the environment which are irrelevant to your task and still make progress. So you will find that, some of the recent papers in, curiosity-based exploration or exploration, they talk about novelty traps and they talk about noisy TV. And this is pretty much what they are referring to. So I'm going to skip the generalization part. This is not required. So the other thing, another question which came up was, well, for these strategies to work, it is necessary that if I optimize for novelty, it ends up aligning with what I want the agent to be doing, right? Or what I want, or the desired behavior. Now, sometimes you might want to combine external rewards that you give, which come from the environment, with the internal rewards which the agent is producing itself. So a common way of doing this is to take a linear combination of the intrinsic rewards and lambda times the external rewards. So pretty much, this is the de facto standard way of incorporating environmental rewards or external rewards. An alternative is also that you can think of exploration methods as just doing data collection, and you can do skill learning on this data. So recall, what we discussed in learning from demonstrations lecture was that we can use expert demonstrations to learn skills, right? We saw this in the case of table tennis, right? How by getting some data from a human expert, we learned the skills of playing table tennis. So instead of using expert demonstrations, if my exploration strategies are good, they can also be a source of data for learning skills. So that's the second way in how these exploration strategies can be used. So putting all of these pieces together, right? So we have our state, we have the policy pi, produces the action AT. Then when we execute the action AT, we go to the next state, right? But we also can measure the prediction error, which gives us the rewards that we can use to train the policy. Right? And these rewards are coming from this prediction module, which takes in states at 2 time points and tries to predict the error in what is going to happen in the future. And now, what you can do is you can ask a question. So, well, how well do these strategies work quantitatively? So one way to do this is you can vary the sparsity of the reward in the environment. Right, so I'm showing you these results from the navigation task, where you have to go from one part of the map to the other part. So just to give some context, because I skipped this. So the task is you're starting from some point and you need to go to some other point. Right? And the sparse reward means that you only get a reward if you reach the goal. Dense reward means that you have intermediate rewards, that you get some reward for coming here, some reward for coming here, and then some reward for reaching the goal. Right? So what you'll see is, in case of dense reward, if we train A3C, it also ends up learning, with intrinsic motivation or with curiosity-based reward, one can learn faster. And as the reward becomes more dense, more sparse, just vanilla A3C, which relies only on external reward, ends up failing, versus these exploration-based algorithms, do significantly better. So this is a general trend you will find in exploration papers as you would read. This is the standard way of evaluation, right? In sparse reward setups, how well do these algorithms work? So now let me take a small pause and see what questions came up. So I think we answered the question, is the prediction in the pixel space? So Dongchi, you have a question about the mismatch between the environment versus the curiosity reward. Did we answer that question?
Yes, I think so.
Okay. The second question you have is about Bayesian reinforcement learning. So I think it really depends on how you are defining Bayesian RL and what setup you are defining Bayesian RL. Right? I think if everything is linear, I think in those domains, I think you can do good exploration exploitation. Sometimes what you say is you measure some notion of uncertainty in your Q function or your reward function, and you use that to guide exploration. So we will look at one work using uncertainty to guide exploration. Right. So one way to look at all Bayesian-based exploration methods is they will estimate uncertainty and use that.
Right.
Right. So we will see an example of that, very shortly.
Thank you.
So, and these methods, like the prediction error method, right? I mean, they don't require you to estimate any probability distributions. Depending on, if you are in a scenario where you can estimate the probability distribution well, maybe Bayesian approaches are reasonable to use.
I
But in
see.
some scenarios, it's very hard to learn a good probability estimate.
I see. Thank you.
Then above you have a comment. This approach is kind of training a model of the environment as well. Yes, so so we are learning the models, and the models we are learning on more and more diverse data over time. But there are works which show that the models that you learn with such data collection end up working better than if you just perform random set of actions and then train the model. Right? And then you can use these models as is for model-based planning. And you can think of these exploration algorithms as ways of self-correcting the model. Right? They're really trying to find where the model breaks and collect data over there so that the model can be improved. So, okay. So what are some open questions with exploration algorithms? I described you one, but we're going to talk about a couple of others. So one issue is that these exploration algorithms are still not a core part of training RL agents. They are an active area of research, but still, if you find the latest and greatest results in RL, they will pretty much use epsilon greedy or some entropy measures. One reason is that balancing this extrinsic versus intrinsic rewards can become tricky, right? Except for some domains. This is something that people are looking into. Then generalization to new environments is limited. You learn to explore one environment, but you don't necessarily transfer this to a new environment. Thirdly, exploration using RL is still data inefficient. And what do I mean by this? For example, if you saw these curves, right, we still require millions of steps, right? Although you could be much better than the baseline, but millions of steps to explore is still impractical in the real world. So what we're going to look in the next part of the exploration discussion is how some of the more state-of-the-art methods are trying to address these problems. So we won't have time to get into that. So what I'm going to do is I'm going to end by saying some different families of intrinsic reward choices we're going to look at. So we looked at one choice was prediction error to model novelty. We're going to look at count-based exploration, which explicitly measures how often you were in the state. We're going to look at learning progress. And there's some others like measuring uncertainty, measuring diversity, so on and so forth. So with that, I will stop and take any questions. So, yes, so Ayush, you have a question. Beyond efficient exploration, safe exploration also seems important for many risk-sensitive cases, but seems counterintuitive to standard definition of exploration. Is there some work on extrinsic and intrinsic constraints there? So there is, work on how to constrain exploration. Now, this is something we will discuss in offline reinforcement learning. So let's revisit this question after the offline RL discussion. I think it will be much more useful at that point. And if that question is not answered, then let's come revisit it. And Siddharth, your question is, does planning with these models mean that we just use the forward model to get the expected rewards and then choose the actions using the planning algorithm? Yes, so the planning algorithm over here was just a reinforcement learning policy, but in general, you can use any planner that you want.